The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you, and good morning to everybody. It's nice to get up at 8:30 in the morning. I'll come up with my talk. So I'm going to talk about not corrosion per se today, even though the samples I'm looking at all had corrosion work done on them. And I will say that they all went into corrosion much quicker than they would have if there would have been no crack. So the crack definitely caused corrosion to initiate early. But I'm going to talk more about how the type of bars and the type of cementitious material you use might affect how fast that chloride gets through your crack. So I'm going to give an introduction to what we did testing, and the testing was mainly done for corrosion testing, but we did look at the chloride contents. Concretes were different concretes, same concrete general mix design, but different cements and types of cement and reinforcements were evaluated. I'll talk a little bit about the test performed, the results, and what our initial conclusions are and where future work would be headed. Now, why are we interested in this? We have several models exist to predict chloride ingress in the concrete as a function of geometry, concrete composition, and exposure. However, the programs do not address ingress at cracking, and the famous words are the concrete really has low ingress of chloride away from the cracks. So the cracking is something we need to know what happens at a cracks and how we would modify our models or what remedial actions we have to take to eliminate the role of cracking so we can use our models. These studies, unlike a few others that have been done in the past, use very good quality concrete, and you'll see that you'll get an idea what cracks formed in flexure to determine the chloride ingress at the cracks versus in sound concrete. And mainly it was done for corrosion testing. And with the type of flexural crack we make, we have extremely large cathode to anode ratios. I'll show you the samples in a little bit. And but we can study the chloride coming through the crack to see what the effect that is versus the sound concrete, and that's what we're going to look at. When I look at effects of cement type, this work has been sponsored by several different organizations. One was NCHRP looking at the various rebars. Another sponsor was FHWA looking at alternative cementitious materials. These are my views, not theirs, but I'm showing you stuff that has been that they know about. The effects of the corrosion performance and the bottom bar effects were determined. You'll see we have a sample that's 6 inches high. We've got a bar on the bottom, 2 bars on the bottom and a bar on the top. The crack, even though it doesn't go all the way down to the bottom bar, actually will have an effect on chloride at the bottom level. So it's not only the top level of the steel reinforcement you might have to be worried about, you also might have to worry about the bottom levels. Corrosion performance was determined at both of those, but I'm not going to concentrate on the corrosion aspects. I can answer questions on it later on because given 20 minutes, you can't do everything. So the concrete steel's advantage, we looked at concretes with a base mixture of 0.4 W water cement ratio, and used to make things. The first study was using ordinary Portland cement. We looked at black bar. You can see the initials, so if you see something later on. Black bar galvanized, hot dip galvanized, epoxy coated bar. We looked at a thermal zinc diffusion coating and also with a lab applied epoxy. 81035 steels with and without calcium nitride corrosion inhibitor, and a duplex stainless steel. Alternative cements, we only looked at black bar on those. We looked at calcium aluminate cement. Another calcium aluminate cement that had a little bit of blend of cementitious blend with some normal OPC, calcium sulfur aluminate cements, and we also looked at a type C activated fly ash. The crack beam macro cell test, as I say, we used mainly it was used for corrosion testing, but you're doing corrosion testing with chloride, so you can learn a little bit about how the chlorides are affecting things. So we had a 0.4 water to cement ratio. If we made beams like this, and in fact smaller beams like this in the lab, they would take years to go into the corrosion. There's no reason when you're testing corrosion in cracked concrete to go to a high water cement ratio and low cover. The crack is going to make things happen a little bit quicker for you. And they don't all go into corrosion at day one, so there is something about that. But you also used 1.5 inches of cover over the crack. So we had the bars were a little bit more than 1.5 inches down, and we had a notch that brought it down to 1.5 inches over the crack. So and the beams were large. These were normal 6x6 flexural beams. Bar treatments, bar and end treatments. We protected the ends of the bar so there would be no corrosion over there, and the dam was far away from the end treatments, so that we're not getting any crevice corrosion occurring at the ends of the bars that could mess things up. But that's for more on the corrosion end. We had unreinforced beams to know what type of flexural strength we had to, give us an idea. The idea of that was that we would crack them to get the right crack size, but later on, every few months, we'd put them into a fatigue cycle at 75% of their flexural strength. So that was a pretty, substantial fatigue. And you didn't have to do a lot of cycles at 75%. And that would be what reflect real life, where you're going to have fatigue in a structure. Once again, the crack sizes were trying to be between 8 thousandths and tenth of an inch, 0.01 inches. These are below what is normally allowed in codes for this structural capability, but for cracking, those are large size cracks, as you'll see. We cycled them 1 week with 3% sodium chloride and 1 week ambient drying. We measured the corrosion current on it and the corrosion macrocell currents, the potentials, and we looked at that, over the crack and away from the crack. It turns out the crack was polarizing. We're not going to talk about the corrosion. It was polarizing the area of 3 inches away, so later on in studies we only bothered to measure it at one place. Schematic of the beam. The beams are actually 20 inches long, so the aspect ratio and to get everything into the figure are not quite exactly what you see here. They're longer than that. But you can see we had a crack, we had a notch, and then in flexure we had a crack. And the nice thing about it is if you have a nice long beam in flexure, it's easy to control. You can get a controlled crack somewhere between 0.08 and 0.01 inch, and it pretty much stopped in this region. They did not proceed down to the bottom of the sample, and we did the ponding, and we had 2 bars on the top, 1 bar on the top and 2 bars on the bottom, like as we see here. Since they had a crack here, and this bar over here is very large, and most of the chloride's here, so we had a very 2 to 1 cathode to anode ratio, plus the bar on both sides of this are also providing cathodic current to where it goes in. So it's a very high cathodic to cathode anode ratio, which you would have in a real life structure. We have only a small amount of steels ever corroding at one time initially. So the results, we'll look at the effect of what different types of reinforcement had, then we'll look at the effect of cement type. So this is looking at this little complicated slide, but basically what we did is we looked at the cracks, top center of the crack at various top center crack, we had various depths. Then we looked at the offset away from the crack, and the first thing you can see on all of these is that at the surface they're not too much different. A little bit more there, but as you go down, you can see the effect of the crack. Also, you can see on almost all of these, there is a decrease in chloride going through the crack for the OPC concrete. So the crack is not a direct short circuit, the chloride coming all the way down at the surface. The cement is the crack's tapering, and there's some interactions between the cement and the chloride coming down. The cement phases got with the chloride coming down, so you don't exactly have uniform crack depth here. And this will be important. Uniform chloride going throughout, and this will be important when I talk about some of the alternative cements. Looking at the bottom center, no crack didn't get that far down, but it's got almost 1.5 times, 2 times the amount of chloride that's away from it. And you can see chloride is slowly coming through the samples, even away from the crack. So I mean, it's but this is also 2 years of heavy ponding. So it's a very severe condition. If we look at most of these bars, did not show any difference at the bottom offset. This TCD has a very porous coating on the bar. It bonds very well, and you can see there was a little bit, at least to an 80% confidence limit, there was a reduction in chloride at that level. We're having more samples, it would be more offset. We were to see, and so that actually was looking like it might actually help the crack close up a little bit. It should be noted with D-stacks and when we flexed them in flexure, we had to put a wedge in there to keep the crack open. The steel was still, we didn't go beyond the yield stress of the steel, so the steel still wants to pull the crack close. So these are tight cracks, so they would actually taper down coming in. So more like, not like a wedge that you just pull up and have a cracked it. These are actually cracks that are the bar wants to do its thing. It wants to close the crack up. And you can kind of see it over there. The 1035 steel showed a slight decrease over here. We would need more samples to demonstrate that. And most of the other bars did not show much of a difference in effect on that. They seem to be close to where the control was or slightly higher. Now, we also did some extra work looking at 1035 bars with calcium nitrite, and we have known from the past, some studies have done that calcium nitrite improves the bond strength of rebar. So I said, what would happen if you had a high-strength rebar and you put something in it that helps improve bond? Well, that's actually, here's the black bar information from a different set of series here. And you actually it's the same series, and you can see the average at the south is pretty high at the top center, at the bar level. And look at these standard deviations, in the order of 10% or less. They're very tight, the amount of crack on samples. It's not like one sample has a very high chloride content, the very one low. They all come out they're all fairly tight if you look at them relative. They're 10% or less than 10% of the amount of chloride there. When you get over up to the bottom center, you can see there's still about half the chloride here that there was at the surface. This is 5 inches down. So it's 5 inches before, it's 4.5 inches, 4.75 inches below the crack, roughly, almost. And you can see tight, once again, tight standard deviation coefficient. With calcium nitrite, you can see a significant drop in both cases relative to control with these standard deviations. This is statistically significant to probably a 95%. I didn't do the exact analysis, but I think it's probably close to 2 times the standard deviations on each of them don't overlap. So when you put them there, so this is probably significant to a 95%, close to 95% confidence limit. So you can see that it doesn't matter what type of bar you have and what you do to the concrete, you can reduce chloride from moving farther down. This is important because if you're talking 100-year structures, what's going to happen down at your bottom rebar level? I mean, this is a 6-inch beam with the bars a bottom inch and off the bottom. It's not terribly different than an 8-inch slab, 100 years of this going on, what you might have with the bar off the bottom. So you might want, so cracking is important, not just for what's going on the top, but also for the bottom bars. And I'm not going into corrosion data here, but a lot of the samples by the end of 2 years had bottom bars corroding. And we saw that by the macro cell current dropping off, because instead of sending current to the top bar, they were keeping the current down for themselves. And occasionally we even saw a reflection of the current where the bottom bars were getting current from the top bars, depending on what we had in the system. So we could actually get bottom bars corroding. In the case of these, the bottom bars were not corroding, but the black steel at about somewhere around 48 cycles or so actually started corroding in the bottom bar. And this, mind you, and these are big differences, big long distance and everything. So that's something to worry about crack. It's not just the top bar, it could be the bottom bars. Now we wanted to look at, so the synopsis of the differential material here is that chloride levels were 3 to 4 times higher at the crack than away from the cracks at the top reinforcing bar level, and that's 1.5 to 2 inches where that bar was located from the surface. So so definitely there's effect of the crack, and so the crack is a severe way of accelerating a corrosion test, but it also shows you how important cracks can be for modeling. Because you're getting, once again, you're getting this chloride down there much faster than your model is going to predict. The chloride levels at the bottom rebar level were approximately 2 times higher in the region of the crack than away from the crack. So the crack is, even though the cracks are pretty much being stopped a little bit below the top bar, they are the effects of that crack are being seen farther down. The chloride values were similar in most specimens except for the chloride below the crack at the level of the bottom reinforcement. In this case, we saw a reduction for the TCD bars, which had a high surface area, and we also saw a reduction for the 1035 bars, which especially when you had calcium nitrite present. And I think this is important for looking at where the rows of cracks might play, what your rebar is something that needs to be considered. This is some samples now coming off for the next part of the study, just to show you what these, we got a little more sophisticated moving in later on, so we start taking pictures of our cores and looking at them. And you can see here, this gives you an idea what a typical, here's our notch, here's the crack coming down, and it's much, and then we stopped. We didn't go, the core came from the back side to get to where the bottom bars were, so we didn't want to go into the back bar. So you can see the cracks arrested. Bottom bar is down here. And we're getting effects of this crack on the bottom bar. Stopping here. And we're also seeing a reduction in chloride as we go down this. So there is some, it's not uniform. This is, and you can see the cracking here is through the area and around the area. It's pretty strong concrete. Now, in the case of one of these calcium sulfur aluminate cements, you can see the crack coming down. It went right through the aggregates because this concrete had much higher strength than that concrete at the time that we did it, and this went through the aggregates as one would expect. Looking at, I believe this is another calcium aluminate sulfur aluminate sample. You can see in this case the crack was relatively small, so it might have done a little bit of healing. You can see some white stuff over there, so it looks like that crack might have healed again. But I'll show you it didn't have much an effect on what the chloride was coming in there. Then looking at another type of another cement, this is calcium aluminate cement. This cement here showed cracking around the aggregates. Later, and now this was after several months of testing, and this material went through a phase change, we believe, which is a calcium aluminate cement, so it wasn't stabilized. So over time, somewhere around 90 days under wet conditions, you get reactions that goes through the crystalline structure of the reaction products change, and you get it. So it ends up being a little bit weaker, and we saw that also on it's only cement based. If we looked at where the permeability, the diffusion went up in time, well, the resist conductivity went down in time. Up in time rather than going down like everything else. So it has, that's it. Now we have another one, that calcium aluminate cement. It had some cement in it. I don't have that data available because we just took those samples out, but that did not do that, and we suspect that's going to look a little bit more like the OPC as far as behavior. Looking at the chloride contents, and since they have a very short wet, they're wet most of the time, half the time, and it's really not drying that much. We figured we'd just plot them on points, on curves, and try to fit them to a bulk apparent diffusion. So it's not 100% accurate, but it's good for illustrative purposes. So you can see the chloride contents and these were not quite as long. This is 22 cycles, which is 44 weeks versus what I showed you before. But you can see you have, which was a 2-year study, but you can see how the chloride's coming down in time, fitting kind of like a diffusion curve. And we get a diffusion coefficient, estimated apparent diffusion coefficient about 3 times 10 to the minus 12. At the crack, we can see obviously about the same, more chloride present, doesn't come down quite as much, and it looks like the diffusion is going up by an order of magnitude. So but it's still reducing chloride coming in the crack with OPC. If we look at calcium sulfur aluminate cements, they had higher initial predicted diffusion coefficient than apparent diffusion coefficient away from the crack compared to the OPC. They're about 8 times higher, about 4 or 5 times higher than the OPC was. At the crack, uniform chloride distribution right through the crack. Done some work on this, and we show that these cements aren't binding any chloride whatsoever. So the water soluble to the acid soluble chloride is practically the same. Makes sense. There's no binding of chloride, and the chloride just comes straight through the crack. So it does matter what cement you're using, because in OPC you still decrease the chloride coming in as you go over the crack, and some of this particular alternative cements, these two ones, there was no reduction in chloride from the surface going down to beyond where the bar was. Looking at a couple others here, the calcium aluminate cement we had. It looks initially it looks a little bit like it's doing diffusion, low chloride, low value, just like the OPC. Actually, a little bit lower maybe than OPC was. When it cracked, Once again, you get a little bit of drop, but basically pretty much uniform and 1.5 orders of magnitude higher. So it's definitely hurting at the cracks. Type C fly ash with activator had a pretty low one to start with, put an OPC, a little bit let at an OPC, but once again, at the crack, it gets much worse. So the effects of cracking on these alternative cements is much worse than the effect of cracking is much worse than what it is for OPC, or much more severe than it is for OPC. So anyway, comparison of the among, we see the pseudo diffusion coefficients are higher for CSA1 and CSA2, approximately the same for the other two alternative cementitious materials. However, the total chloride at the surface and subsequently in the interior is less for the ACMs, which is yet to be determined. At cracks, all the ACMs except the CAC2, which I didn't show, has no effect on depth of crack, whereas there's a decrease in chloride with depth for an OPC. In overall conclusions, OPC concrete had a relatively good low water cement ratio, 1.5 inch of cover. Structural cracks showed the following behavior: reduction in chloride as a function of depth, increased chloride ingress at the reinforcement, approximately 3 to 4 times that in sound concrete. Apparent bulk diffusion increase, approximately 1 order of magnitude. The reinforcement can affect chloride ingress to the bottom level bars and 5 inches from the surface. Calcium nitrite with A1035 bars, reduced chloride at the bottom of the bar level. Makes sense. These high strength bars, better bond. They can hold it. They can keep it from chloride from getting down. And the coefficients of the variance were surprising to me when I looked at it. When I was putting this study, I didn't look at it closely, but they're low. I mean, this is pretty reproducible, at least on the same day. I won't say it's going to be close for one set made today and one set made a year from now, but within their set, they're extremely good. Conclusions continue. The alternative cement studies showed significantly larger chloride ingress at cracks relative to sound concrete than OPC. Chloride was not reduced as depth increased, so that means they could go into corrosion faster. Matter of fact, on some of these we found not that much top bar corrosion. We have on a good portion, the bottom bar corrosion was about as high as the top bar corrosion. So and that's for those of you who just look at macrocell, you got to look at the sample later on and actually look at your bars, because that tells you an awful lot, especially when you see your macrocell current dropping after it was high for a long period of time. That's almost a dead giveaway that it's dropping, because the 2 bars on the bottom in this particular test are corroding. Next steps: complete the analysis of the ACMs that were not included here. We just took them all out of testing, so I have a report for my part of the FHWA report is going to be due pretty soon, so maybe next year I'll be able to present it here or somewhere. Model chloride transport in the cracks, that's our ultimate goal, to find out how that's going to be, and we like to, down the road, look at how SCMs affect this, so basically fly ash, silica fume, metakaolin, and alternative pozzolans. And thank you.